To analyze the AC signal performance of this amplifier, let's see what is happening to the signals when we insert or inject an AC signal, right? So similar to the BJT when we apply a AC signal through the coupling capacitor, so that the DC biasing would not be disturbed by this signal source. Here we would be having DC and AC both, right? Here also only AC signal would be coupled out to the load. DC will not see this resistor, right? But here we would be having both. So we have already said VG, VD, VS and all other things accordingly to set a Q point on the load line. Okay, and for amplifier it would be in the saturation region. Now if we insert a V signal, then this AC signal will be coupled to this circuit, and for the time being it is coupling at the gate, right? So it means the part of this signal will be appearing on this resistor and part would be appearing on the resistance, the input resistance of this stage, while looking into this side where the AC signal is being injecting, right? So it means part of this signal would be added to VG, right? And it becomes VGS. So it means we already had V DC VGS, right? Capital V, capital G, capital S, right? And this AC part of VGS, small v, small g, small s, will be combined to make a total VGS, small v, capital GS, right? So it means overall VGS is changed, right? And for that changed VDS, as per the input characteristics curves and the output characteristics curve, we would be having a change in ID and change in VDS, right? For example, for an increase in VGS for this NMOS and for this common source amplifier, when VGS increases, the total VGS, right, increases, ID increases. ID increases, voltage drop across these resistances because ID is through this one and this one. ID multiplied by this, ID multiplied by this voltage will be increased, right? So the overall division of this 5 volt will be appearing more to these resistances. It means VDS is decreasing, right? And we are having a output of negative phase, right? Remember, in common emitter amplifier we are always having a 180-degree out of phase shift, right? We have amplification but with 180-degree out of phase with the input signal, right? So same would be here in common source amplifiers, right? So for an increase in VGS you will see a decrease in Vout, and for a decrease in VGS we will get an increase in Vout, right? So for example, if we insert a particular value of V signal, right, part of this would be divided here and part of this would be dividing across the input resistance. Combination of these things we will see later will be appearing at the input of this stage, right? And that signal is actually part of that is becoming VGS, AC part of VGS, right? For example, this is the AC part of VGS, right? This is the AC VGS, right? So it is 75 millivolt. And suppose we already had a DC VGS as 1.836, right? So it means the AC will be fluctuating about this DC. So the total is this one, right? This is total. This is total, right? So what will happen? You have basically decided a VGS. This is the VGS, and VGS would be greater than VT. How much greater than VOV, right? Fine with the graphical representation. And when we insert a V signal, part of this will be becoming VGS. So this is the AC VGS, right? AC VGS. And when this AC VGS is there in this circuit where we already had a DC VGS, it means this will be added with this one and make a total VGS, right? That's why this VGS point will move here. So it can only be moved because this transistor said this is my response. If you increase VGS, you will get an increase in ID. If you decrease your VGS from this point, let's say from to here, you will get this ID, right? So it means the transistor will be behaving how much voltage instantaneously I have on my gate to source, right? And he will provide ID accordingly. And remember, it can provide ID when we have applied a VDS, right? It can create the channel, but current will flow only if VDS is set to some value. In here, it would be in the saturation region, right? So for small signals, this variation, this movement of Q point, DC Q point, will be linear, right? Otherwise, this curve is non-linear. For large signal, you will not get a linear amplification, right? So as you apply this AC signal, total VGS increases, total ID increases, right? This is DC ID, this is the AC ID, and you have a total ID, right? So this is total. But if you subtract it from this DC value, only see this peaks, consider this as 0, and this is only the AC signal. So when this ID changes, if you already applied a VDS, that change ID increases, right? ID increases, right? So ID increases from here to here, right? So ID increases, but the load line of this output side is saying that I can move along this line, right? Which has a negative slope. So it means if ID increase, VDS decrease. So you have this amplitude output for this input. Increase input, you have a decrease output, and so on. This is the same thing we had been teaching for BJT, especially for common emitter amplifier. But I explained you again so that you have a revision of that thing, and now you have a comparison of that thing with this one. Okay. So AC small signal modeling can be done, right, for a small signal, right? So I'm not going to drive as we drived in BJTs, but here I will show you only the formulas, right? And also the derivation is also not included for this MOSFET for small signal modeling, but for BJT it would be included. So neglecting the dependence of ID on VDS in saturation, the channel length modulation effect, actually when we reduce, we have this relation of ID in saturation region, right? If we have channel length modulation effect, the early effect, we would be having another parameter, 1 plus lambda something, right? And we know that this is DC VGS, but when we insert AC signal, then part of that AC signal becomes VGS, AC VGS, and then the transistor will feel a combined signal of these things, the total VGS, right? And then if this VGS is less than 2 VOV, right? VOV is set by taking this DC VGS higher than VT, right? And twice of that VOV will tell you that your signal VGS is small. Less than this one would be considered as small signal, and then you can use this model which we are going to introduce. Okay. So if this is your VOV, right? And if this is VGS AC, this should be very less than this one. Then you can use these models. Okay. And what is the formula of GM for MOSFET? In BJT, we had IC over VT, right? Here we have GM is equal to 2ID over VOV. Okay. and this is the model, right? VG the same. At that transistor we had an emitter here, base here, collector here. We had a input resistance R pi, but here gate is isolated, actually insulated, right? No gate current. It means we don't have any resistance here, an infinite resistance, right? And the same thing, drain to source, a current source would be generated for a constant value of VGS, right? Okay. And as VGS increase, this current will increase. As VGS decrease, this current will decrease. So will be the voltages will be changes, will be changing. So now if we include the channel length modulation effect, right, we can drive this whole thing again with that formula, or we can still use this model but just model the R naught, right, as we did previously, right? But R naught, how to introduce this? The book provide this thing that you can use in start from here and then go to find this thing. But as I told you in VJTs, you can neglect initially, you can find the IC neglecting by neglecting the early effect, do everything, find GM and everything. But when you are going to use the model, put an R naught. If you put that R naught and then you use that R naught in your gain calculations, it means you have considered the early effect, not from the start, but at the time when you analyze the AC signal performance of AC signal performance of the amplifier. Okay, so you don't need to use this formula from the start, right? You have just to you just have to calculate this thing and include here. Same as we did for BGTs. Okay, so this would be the T model, right? This is the pi model, this would be the T model, right? So pi model you don't have any resistance, but T model you had a resistance, right? It's actually 1 by GM, right? Why? Because this current is this and this current is same, right? So if you had a resistance here, then resistance divided by the conductance will be equal to, sorry, voltage divided by conductance would be the resistance, right? Why we model a resistor here? Because we may include a resistor at the source, and this model will be recommended, the T model, when you have a source resistor. Otherwise you have to use pi model. So next we will see the discrete circuit amplifiers.